Now we're going to say a few words about the cosmic neutrino background. Uh, from the continuous spin states and something called photon reheating, we find that the number density of neutrinos and number density of photons uh, are comparable. It was the comparable number of relic neutrinos in the cosmic neutrino backgrounds and as uh, relic photons in the CMB. And also neutrino contributes to the cosmic radiation energy uh, about two-thirds compared to the value contributed by the photons. So for their energy density coming to be neutrino density is about 0.67 of the photon density, energy density. We have already discussed the CMB formed from decoupled photons. There's another cosmic background of comparable abundance formed by decoupled neutrinos. Neutrinos have only weak interactions. Their collision cross-section with the other particle, for example, with electrons, is extremely small. But these cross-sections have very strong energy dependence. It was at extremely high energy, they have somewhat measurable cross-section, but once you go low energy, the energy factor goes to zero. The early universe high energy neutrinos interact strongly enough with cosmic particle soup to be in thermal equilibrium. So they play a role in keeping neutrons and protons in equilibrium until the freezing out at freeze out temperature, thermal energy of 1 MeV. Sure thereafter, when the temperature fell to about 0.3 MeV, they decouple, become free streaming. Okay. This cosmic neutrino background was formed considerably earlier than the microwave background, decoupled photon. That was happen at 0.36 electron volt. Okay, 0.36 versus MeV, million electron volts. 300 electron volt versus 0.3 electron volts. So I just noted this particular three period about when the cosmic time of 1 second, when the freeze out temperature is 1 MeV, neutron proton ratio basically get fixed, and they no longer interchangeable, so they fixed to about 1/6, and compared to the 0.3 MeV neutrino get decoupled. Okay, neutrino slightly later at 0.5 MeV, about cosmic time of 4 seconds, photon get reheated. We explain how it goes through the annihilation. Electron positron gave the cosmic photon a boost of the temperature compared to the previous decoupled cosmic neutrinos. And remind you, about 100 seconds, you have the thermal energy of a tenth of MeV. You have the Big Bang nuclear synthesis, and at 380,000 years, the thermal energy 0.3 electron volts, photon get decoupled. Okay, so first let me talk about this period of time, the so-called photon reheating. We're going to boost photon temperature by electron positron annihilation. Remember we said radiation temperature scales like 1/A. Regardless of whether the particle are coupled or not, thus one expect the temperature of a cosmic neutrino background to be the same as the photon, right? Because whether they couple or decouple earlier doesn't matter because the temperature always scales like 1/A. However, their temperature not exact same in this case because in between neutrino photon decoupling time, the photon temperature got a boost from electron positron annihilation. Okay, electron positron annihilating photons. As a result, the photon temperature is somewhat higher then the neutrino temperature, higher than other would have been without this reheating. So it would be higher than the neutrino temperature. Okay? And the calculation was then exercise 9.4. So in the end, after reheating, the photon temperature is higher than neutrino temperature by a factor 11, cubic root of 11 over 4. So given the fact that the CMB temperature now is 2.7 Kelvin, so the cosmic neutrino background now has a temperature of 1.9 Kelvin. Now knowing this temperature, let's define what is the neutrino's contribution to the radiation energy density. Remember, knowing the temperature, thermal temperature, you can find the number density for bosons, and it's slightly different for fermions. Neutrinos, fermions, and photons, bosons. And G is the spin multiplicity. So therefore, you take the ratio of neutrino density over photon, what you get is this three-fourths factor, and then the temperature factor, and then the spin factor. And for photons, G multiplicity is 2, and for neutrino is 6, because there's left-handed neutrinos and right-handed antineutrinos, and there are 3 flavors. So left to right, neutrino, antineutrino, there's 3 flavors, so altogether 6. So you plug this number in, you get this 9 over 11. Okay, so that's the ratio of the neutrino density over photon density. So they're comparable. And so if your photon density is 410 per cubic centimeter, so neutrino is about 335 per cubic centimeter. Now we can translate this into the ratio of the energy density. Stefan Bols-law, the energy density proportional to the 4th power of thermal temperature, and G star is the effective spin degree freedom, which we had talked about before. Here is the boson, here's fermion, and here's the sum of all the species. Okay, and again, you find there's different calculation than the book will calculate these factors, and then you plug in and the effective spin factors and the 4th power of temperature, you got the ratio to be 0.68. So it was to the radiation energy content, the relic neutrino contribute about 2/3 as much as the relic photons. By by the way, you see there are all these neutrinos around. We have detected the relic photons. What about detecting the relic neutrinos? Well, that's because neutrino crossing is so small. No one has any idea how to ever detect this. Okay, so anyway, so uh, here's a physics assignment. You go out, find a way to detect neutrinos all around you. There are about 300, 400 neutrinos per cc all around you, in your body and out. And if you find a way to detect, you're sure to get a trip to go to Stockholm. Here we do a problem. Remember we said early universe was radiation dominated because radiation goes like 1 over 8 to the 4th power, and then taken over by the matter dominant. So when is the time the radiation dominance stopped and the matter dominance began? So this is called the radiation matter equality time. So the matter goes like 1 over cube, the radiation goes on 4th. So to calculate the radiation energy equality time, let's define what I mean by the equality. Define when the radiation density is equal to the matter density at this time. What we're going to do first, we'll set out to find what is the scale factor at the radiation and the matter equality time. So it's called ARN. So this by definition they are equal at this time, and and then because radiation scales like a to the fourth, and the matter scales a to the cube, so therefore they are related to the radiation density now and to the matter density now by this different factor a. That's the radiation. So therefore, the A at Rm, A sub Rm is from this formula is equal to density of radiation or density of matter, but it can write in terms of density parameter because they both divide by critical density. So it's omega r over omega m at now. So we can relate the ratio, density ratio now versus to find the scale factor when radiation matter took place, equality took place. So how we're going to calculate from this? Knowing this formula, so the fact this radiation is composed of neutrinos and photons, so including neutrinos is 1.67 times the photon density, and then I multiply by omega the baryon density parameter now, and divide by the same number in the denominator. And now take 1.6, this omega gamma, which the parameter is equal to number density times the energy of photon at now, versus the baryonic density ratio, which is the number density times the energy of the baryon at now. And what's left over is this, I just copied over here. Now, the ratio of photon to baryon now is uh, is 0.6 10 to the minus 9. So therefore, this ratio is 10 to the 9 over 0.6. And now this we're talking about photon energy now. Remember, photon energy at decoupling is 0.7 when the scale factor is 1100. So therefore, the energy density now is this have divided by, because energy scales like 1 over a. So divide by 1100. So of course the density, photon density energy is much lower because it's only corresponds instead of 3000 degrees to 2.7 Kelvin. And the baryon energy, of course, is the baryon rest mass energy, which is 939 million electron volts. So I put in, if it were put in units electron volt, 10 to the 6 electron volt. And the baryonic density parameter, remember, is about 5%, and matter, including dark matter, is 0.32. Okay. So you put all these numbers in, you find it's about 3/10 to the minus fourth. Okay. So it's even smaller than the. Remember, the photon scale factor at the photon decoupling is about 1,000. So this is even smaller. So so anyway, clearly she shows this. We are in the matter dominant universe now, and so it was the universe matter dominator since the radiation matter equality time, which a equal to because since then the universe scales like a to the, but as a matter dominator is t to the 2/3 power. So from this, you plug in so the time ratio is the scale ratio is given by this time ratio, and then you plug in the fact that the cosmic age now is 14 billion years, and so you plug this in, you find that's the the cosmic time when the radiation and matter are equal is about 73,000 years, okay, versus cosmic time 380,000 years. So the radiation, the matter domination started uh, way before the photon decoupled. Okay. So here's the lesson we learned in lecture number 24. Oh, it should be 26. Sorry, this. Uh, when the universe was around 380,000 years old, photons ceased to interact with matter, began to pass free through the universe. This primordial light remained today as the cosmic microwave background with a blackbody spectrum of temperature of 2.725 Kelvin. Similarly, in the early cosmic epoch, neutrino decoupled to form a cosmic neutrino background. Thus, the most abundant particles in our universe are relic photons and neutrinos, each with a density about 3 to 400 uh, uh, particles per cubic centimeter. And the radiation matter equality time happens to be around 73,000 years after the Big Bang, and with a scale factor of 3 to the 10 to the minus 4th. Again, this should be next lecture should be 27. The CMB is not a perfect uniform. Anisotropy results from the empirical density unevenness, uh, uh, and this is showed because the uneven density through gravitational clumping form the observed structure observed in the structure in the universe today.